For our next problem, this is an investigation problem. We are given with an to calculate the ultimate moment capacity of a reinforced concrete rectangular beam with the width of 280 millimeters wide and an effective depth of 510 millimeters. The beam is reinforced for tension and compression, and the tension steel area is 5,089 square millimeters, and the compression steel area is 2,035 square millimeters. The compression steel is 65 millimeters from the extreme compression of the concrete, and we are asked to assume that Fy is 400 and F prime of C is 35. Okay, so first thing is we have to examine whether your beam is really a doubly reinforced beam or if our compression reinforcement is really necessary. So for us to investigate it in a investigation problem, given your steel areas, we will solve for your steel ratio, wherein for us to consider this is doubly, your actual steel ratio must be greater than your maximum steel ratio. Okay, so for your actual steel ratio, that is your actual steel ratio of 5,089 square millimeters divide by the area of your concrete, which is your base times the depth, which is 280 multiplied to 510. Your actual steel ratio is equal to 0.03564. Okay, now, what is your maximum steel ratio? This is 0.85 of your F prime of C multiplied to beta 1 over Fy times your 600 over 600 plus Fy. This formula is just for your raw balance for us to have the maximum steel ratio that is 75% of this. Okay, so consider your beta 1. Remember that your F prime of C is 35. So since that is greater than 30 or 31, your beta 1 is equal to, so your beta 1 would be equal to 0.85 minus 0.05 over 7 multiplied to your F prime of C minus 30. So this would be 0.85 minus 0.05 over 7. Your F prime of C is 35 minus 30. So your beta 1 to be used is 0.814% or 0.814. Therefore, your raw maximum is equal to 75% of 0.85. Your F prime of C is 35. Your beta 1 is 0.814. Your F prime of C is 400 over multiplied to your 600 over 600 plus 400. Therefore, your maximum steel ratio is equal to 0.03089. So this is less than your P actual. Therefore, this is a doubly reinforced beam. Since we have proved that our beam is a doubly reinforced beam, so this is your AS, which is equal to AS1 plus AS2, located at the distance T, or effective depth, and AS prime is located at the distance D prime. Okay, so since we all know that this is a doubly reinforced beam, we can now solve for your A and the value of C in order for us to know whether your tension reinforcement or the compression reinforcement is yielding or not. Okay, assuming that our AS prime is equal to AS2, we can have your AS1 as your AS minus AS2, wherein this is equal to 5,089 minus to 2,035. So your AS1 is equal to 3,054 square millimeters. Okay, so having that, we can assume that your T1 is equal to C1, or this is AS1 Fy 0.85 F prime of C AB. So your AS1 is 3,054, Fy is 400, 0.85, your F prime of C is 35, your A, and your B is 280. So the value of A is 146.651 millimeters. And your C is equal to, so we will divide this by your beta, which is 0.814, that your C is equal to 180.097 millimeters. Okay, so we will solve for your Fs. Your Fs is equal to 600 times T minus C over C, which is equal to 600 times your D of 510 minus C of 180.097 over 180.097. Your Fs is equal to 1,099.084 megapascals. This is greater than your Fy, therefore tension yielding. Tension yields. Okay, next let us solve for your Fs prime. That is 600 multiplied to your C minus your D prime over your C. This is equal to 600. Your C, what is the value of C? That is 180.097 minus the D prime of 65 over 180.097. Your Fs prime is 383.45. And it is observable that this is less than your Fy, and compression does not yield. Okay, Since we already know that our beam is a doubly reinforced beam and tension is yielding but compression does not yield, we have to solve again for the value of our A and the value of our C. And the formula of T is equal to C1 plus C2, wherein your T is equal to AS Fy because your tension is yielding, and for C1 that is 0.85 F prime of C AB plus your C2 which is AS prime FS prime, wherein your FS prime is equal to 600 multiplied to your C minus your D prime over C. So having this formula, this would give us AS Fy 0.85 F prime of C. Your AS can be solved as your beta 1 of C times your B plus AS prime. Your FS is 600 times C minus D prime over C. Okay, so this formula, you have your AS of 5,089 times your Fy of 400 and we have 0.85. Your F prime of C is 35. Your beta 1 is 0.814 of C times the base of 280 plus the AS prime of which is also equal to AS2 of 2035 times 600, your C minus your 65 over your C. So the value of C is the value of C is 183.813. Therefore, the value of A is equal to 156.241. This is in megapascals. So therefore, the value of Fs prime is equal to 600 multiplied to 183.813 minus your D prime of 65 over 183.813. Therefore, Fs prime is equal to 387. Still, this is not yielding. 828 megapascals. Okay, now, since that is not yielding, we can now solve for your MU. Wherein your MU is equal to your C1. Your moment arm is D minus A over 2 plus your C2. This is over phi, since this is just nominal. C2 is equal to D minus the D prime. Okay, so your MU is equal to your phi, which is 0.9. Your C1 is 0.85 F prime of C of A, B, D minus A over 2 plus your AS prime, Fs prime, D minus D prime. Okay, and this would be mu 0.9. 0.85, your F prime of C is 35. The value of A is 156.241. The value of B is 280. The value of D is 510 minus A over 2. Let's just say it's A over 2. AS prime is 2035. FS prime is 387.828. Multiply to your D, that is 510 minus your D prime of 65. Therefore, your MU is equal to 821.965 kilonewton meter. That is your ultimate moment capacity of your doubly reinforced beam.